right, good evening, everybody. Welcome to this month's meeting of the Astronomy Club. Good to see everybody here tonight. We have two member presentations tonight, and we have a main speaker as well. And so it should be a fun evening. And we always have snacks and stuff, so that's a good thing as well. So anyway, let's go ahead and get going with here tonight. So I guess I need to get focused. There we go. All right. So standard slide, you see it every month. So anyway, for those in the room, for those that are here via Zoom as well, we thank you for being here tonight. And as always, we hope you enjoy yourselves. We hope you learn something interesting from our presenters tonight. We hope you make a new friend. I met two new people tonight. I met Brad and Noah. So anyway, and we hope you reconnect with some old friends. And I don't have any old friends in here. They're all young people. So anyway, all right. And as always, we want to turn our cell phones onto stun. All right. First things first, we have visitors here tonight. If so, we'd like to meet you ever so briefly. And obviously, we're going to make it very simple. What are we looking for? Your name, how'd you find us, those sorts of things. And we'll put you on the microphone if you want to introduce yourself, because we have folks out there on Zoom that can't hear it unless you're talking to the microphone. So anybody want to raise your hand and introduce yourself? First times or anything like that? Okay, we got one. Okay.
Name's Chris, not a member, just heard about this place, just getting into astronomy recently, and brought my niece with me.
Okay.
This is my uncle Chris, and he has a telescope, and we find it to be wildly fun to do stuff in the backyard with that. So we're just here to learn more about it.
Okay. And according to your shirt, you're just here for the food. So, okay. All right. Anybody else like to introduce yourselves? Oh, right over here.
This is our first time. We're interested in space. She loves space and is going to college, and she's taking space next semester. So we thought we'd come.
Welcome.
Welcome.
Two more.
Yeah, my name's Luke, and I'm going to pull a telescope out of the closet that's been there for about 20 years. Get started again.
Well, welcome. We had a couple more over here. Amanda.
My name is Jan Michael Corey. I'm a master mechanic. I study motion, and I'm very interested in planetary motion.
No, my name is Robert Withers. I've been, my brother-in-law invited me along tonight. He's been here before. This is my first time. I'm from Colorado, so. And what is my favorite thing? I like solar stuff.
Okay.
So I have a solar telescope. I'm trying to learn how to use that.
Okay. Whereabouts in Colorado? I'm just curious. Okay. Yeah, I lived up in the Denver, Boulder area for a good long number of years. So, okay. Anybody else here tonight would like to introduce yourselves? All right. Well, welcome to all the new folks tonight. If you're a member here or someone who's a regular, hunt these folks down during the break and talk to them for a while and find out more about them. All right, tonight's agenda. So we have some general announcements. Same ones you always see, but I've cut down the slides a little bit, so I think it'll go a little quicker. We're going to talk a little bit about public outreach. Actually, our young lady there in the back who's waving at us, she'll be talking to us about public outreach, and we have a little bit about news about some events as well. We have a couple of member presentations. Alice, once again, is going to be presenting on the Seestars. She's had both the Seestar 50 now for a while and the new Seestar 30 for a bit as well. And she's been sort of doing a comparison of the two. So she's going to talk to us a little bit about that. Gordon Rosser, also in the back there, is also going to talk to us a little bit about telescope collimation and how to tell if you need it or not. And then we have some other things to talk about regarding collimation as well. Then we'll take our normal seventh inning stretch. We'll have our break. We'll get our speaker all set up while we're on a break. We'll let you guys socialize for a few minutes, and then we'll have our main speaker tonight, Dr. David Williams from ASU. And as you can see, he's going to talk about the NASA's PSYCHE mission. That's what he's going to talk about. So anyway, so there's our agenda tonight. So let's get ahead and get to it. Are you a joiner? If you are a joiner, then join the club. And I noticed a couple of people actually did that tonight, so that's a good thing. And you can do it here at the meeting at the back table with Brooks, and some of you did that tonight. I saw you doing it. Or you can actually do it off the EVAC website as well. We do have a website. You can Google it and find it. And it actually has a join button on the website, and you can just go through and follow the directions and join the club that way as well. Once you joined, how do you find out what's going on? 4 ways to know. You can sign up to automatically receive what's going on. Do we have an echo? Is your computer? It's always on. Testing, testing. Okay, maybe it was mine. So anyway, all right. So you can sign up for our mailing list. We don't spam you. You get probably 5, 6 emails a month at the most. And what happens is automatic in your inbox, you get event information about what's going on. So there's one thing you can do there at our website. You can actually manually pull information off our website as well. So if you don't want something automatically just shipped to you, you go out there on our website and we have an events and meetings page. And we have a calendar on that page. You can click on anything and bring up that event and see what the details are for those particular events. You could also have set up where you can automatically or manually pull down our newsletter. So if you join our mailing list, you'll get a newsletter once a month, which tells you kind of things that are going on. But you can also then go back to our website, and anytime you want, you can just pull up the newsletter or past newsletters. You can pull up newsletters from 10 years ago. So there's a long line of newsletters out there. And then also, you can also set up to manually get EVAC and member announcements from Facebook. So you can always join our Facebook page. I looked at it actually just a couple of days ago. I was curious. We're up to about 1,100 people actually on our Facebook page now. So it's quite large. So anyway, you can sign up for that and get information. You can also do other things as well. You can post photographs that you've taken during the week. You can say, hey, I'm going out to Picket Post. Anybody want to go out to Picket Post and do some observing this weekend? People sell telescopes out there. All sorts of things happen on that Facebook page. So those are different ways you can find out what's happening. If you need a telescope or training on how to use a telescope, we do have on our webpage also, if you scroll down the home page a little further down, there's a little section here. I've got a copy of it where you can actually click on used equipment for sale or equipment for rent. And it's a good way to kind of get equipment at like bargain basement prices. So most of the telescopes are safely probably about half price. And then, of course, you can always rent as well. Very cheap to rent. And that way you can kind of try before you buy and see what you like. Try a reflector, try a refractor, try, a go-to, try a manual one, see what you like best by renting first. We also have self-paced online information. So also at our webpage, we have this thing called a virtual beginners lab. Every one of those buttons you can click on, it will tell you a little bit about that subject in astronomy. So that's available as well, okay? We also have hands-on classes. Are you still running yours right now? Okay, so James here actually runs online classes as well. Like I said, the next one will probably be fall because let's face it, it's hot in the summer. So we don't want to be out there in 100-degree heat. But anyway, you can always sign up for a class and learn how to use a telescope through James's class as well. So whether you want to do it online on your own or through a class, we have both available for you. Our charter, Alice, is to give back to our community here. So I'm going to turn the mic over to Alice here for just a couple. Events coordinator here at the club. And so that's why she's going to talk about events and things like that.
Awesome. Thank you, Steve. Like Steve said, I am the club's event outreach coordinator. So what the great thing is about our club is we have 2 ways that we like to give back to our community. And the first one, see if I do this right. Yes. The first one is just down the sidewalk over here at the Gilbert Observatory. So the Gilbert Observatory is owned by the city of Gilbert and the East Valley Astronomy Club. We manage it and operate it, and we volunteer there to do that. It is open every Friday, Saturday night, weather permitting, from sundown until 9:30. Now, what do you do volunteering there? Well, you can learn how to operate the telescope, or if you're like myself, I'm not really into operating the telescope, but I enjoy entertaining the crowd. So what I do is exactly that. Let the crowd know what telescope etiquette is, let them know what we're viewing. And then if it's a longer line, then I just give them like a 101 astronomy class, like what is the ecliptic and what are the constellations up there? What's the big deal about the North Star? Now, let's say you're like, hey, Alice, I don't want to have to do that. Well, we need someone to work the door. We have a clicker, so we know how many people show up a night. You could just stand at the door and operate the clicker and then talk to the people who are just getting ready to come in. It is a fun time. I have learned so much from our other fellow volunteers and from our guests. So it's a great way to give back to the community. You can choose how often you would like to volunteer and when you want to volunteer. As you can see, there's the email. You can contact Claude and let him know, hey, I'm interested in volunteering, and he'll get back to you. Now, my event is giving back through outreach. This would be schools, HOAs, libraries. So what do you do there? Well, you volunteer your time and a telescope, and you go to these events and you just share your love of astronomy with the guests there. You would, if you have a telescope, you'd show up having something in mind of what you want to share, like for instance, Jupiter. And then when guests come up, you say, hey, I'm looking at Jupiter and can you see the storm bands? Or if you don't have a telescope, Gordon and I are calling them walkers, but I can always use somebody helping out to manage the crowd and our guests to remind kids, hey, let's not run, or we don't have food or drink in line as we're waiting to go up to the telescope. Also helping with the telescope operators, hey, are they doing okay? Do they need some help? So it's usually about an hour, hour and a half at the event. It is so much fun. If you're interested in doing it, please sign up on the mailing list, which is right up here, the free list. I do everything via email. I will send out at the end of the month, the next month's confirmed already star parties. Then I also send out reminders of what star parties are coming up for the next day. Also any cancellations. If weather cancels a star party, then I'll let you know via email. So please do sign up if you're interested on that free list. So let me share with you what we've done so far. So we went down to the Santan Valley Library. It was a blast. It was a smaller crowd, which was nice because we had more time to interact with the guests. Our next one was at the Superstition Sleepover. So over here at AJ, Apache Junction, they hold a sleepover at one of their big parks. And so guests came over on a tractor with hay bales, and they came over and viewed through our telescope. It was a fun night. We made it work because the clouds were coming in and out, but everybody had a blast. Next was Playa del Rey Elementary. This was pretty cool because it was one of our members' kids' school. So it was kind of fun to share the club with the entire community of the school. What was happening here was it was reading under the stars night. So the kids would go get a book. They had a blanket out on the grassy area, read for a bit, and then they'd come over and view through the telescopes. Then our latest one was the lunar eclipse. I believe that was last week. That was actually quite fun. Claude got special permission from the park ranger to stay open later, and we had about 20 guests show up. It was quite nice because we had time to interact with them and to hang out, and it was nice to interact with our other members that were there. Our regular volunteers, outreach volunteers were there. We had David and Don and Josh. They all showed up with their telescope, and then we had a non-member show up with his Seestar, and so guests were able to see the lunar eclipse through 5 telescopes. Yeah, it was really quite nice. And then, there we go. Yeah. I actually took that picture with an iPhone through Josh's telescope, through his eyepiece. All right, upcoming star party events are right there. You can also check on our events and meetings tab on our website at our calendar. And again, if you wanted to help volunteer, please sign up at the free lists. And, all right, here you go. I'll hand it over to Steve. And then if you guys had any questions about volunteering, please come see me at the break or after the meeting. I'm happy to answer.
Don't go too far. We'll be back up shortly. So she'll be back in just a couple of minutes. She's got a presentation going. So anyway, we have a couple events here. Let me back up. So we have some events to talk about real quick here. Number one, at the end of this month, we have actually next weekend. Now I think about it. A week from tonight, now that I really think about it, we have the Messier Marathon out at the Hovater Road observing site off the I-10 freeway out towards Quartzsite. So we're out there Friday and Saturday, March 28, 29. It's actually the Saguaro Club's event, but we always join them. They usually join us at our events. We sort of do a group thing out there. And we are going to be out there. I will be out there. They've asked if we could do, we do the coffee and cookie table for the 2 nights we're out there. So they'll provide dinner on Saturday night and all that, but we do some things to help them out as well. So we'll be out there. So if you want to come on out, come on out. There'll be a bunch of us there at least. I know Jeff said he's going, I'm going, Allison Gordon will be there. I know several people said they're going to go out for the event. So that's available. Also on that same weekend, but just on Saturday, if you'd like to go up to the Fountain Hills area, the Fountain Hills is doing their annual Fountain Hills Dark Sky Festival. They're really going to town out there, actually building a big observatory out there. They're actually really involved in astronomy out there. Anyway, they've run this event multiple years now. I try to go most years. I can't do it this year because of the Messier, but it's a lot of fun. Literally like a few thousand people show up to this event. There's food trucks, there's lectures, there's displays inside the library out there to look at it. It's quite the event. So if you'd be interested in going there, there's some of the details. You can, of course, Google it online as well, the Fountain Hills Dark Sky Festival, and gives you some of the details about the event itself. It's a lot of fun. Also, there's a bunch of us that are volunteering all the time. You saw volunteers there in pictures when Alice showed you what we're doing here for at the various schools and HOAs and whatnot. Other people help in other ways, but we implemented this thing called the Starry Rewards this year. A lot of you are accruing points now towards that. Things for luncheons and other little giveaways we're kind of doing as part of that program. Anyway, we finally set a date for the actual luncheon for those that qualify for it. We're actually going to buy you lunch, and it'll actually be just about a mile down the road here at where are we at? We're at Greenfields with Higley and Guadalupe North. East corner, there's a Mexican restaurant there called Rancho de Tía Rosa, and we'll have a lunch there 12 to 1:15 on August 11th. So I just mentioned that, saying, hey, we'll see some of you there because some of you are actually accruing enough points to qualify. Also, we wanted to take a straw poll here. There's been mention of maybe doing some sort of a more family type picnic. So just not maybe a night event, but something a little bit more during the day. So one of the suggestions was Peralta Regional Park out there because it's fairly dark out there. It is actually behind a hill compared to where the Phoenix Valley itself is. We did do a star party out there. Oh, we are? Okay, well, we did one last year. It's kind of an interesting area. You can actually camp out there, but the idea is we could, theoretically rent a gazebo and all that and kind of have more of a daytime event. Might be of interest to you, might not be of interest to anybody, but we'll thought, show of hands, anybody would be interested in something like that or not really? So a few. Okay, all right. So we'll give that some thought. We'll see if we want to do that or not. One other thing, I don't have it on the slide deck, but I do want to mention this. Last meeting, we had a sign-up sheet on that table there where the T-shirts and the hoodies and all that are at. And several of you signed up for hoodies and zippered, hoodie, EVAC logoed shirts. They have been ordered and we should have them here at the next meeting. So anyway, I don't have the price yet. I was hoping the guy would get back to me by today finally, but he did not. So I don't know the price of them yet, but I think they're under 300. So no, I'm kidding. No, anyway, no, I don't know. I'm sure they'll be in the $20, $30 range. I'm sure for a nice hoodie. And I don't have mine. Oh, actually, Alice is leaning against mine. So anyway, but that's kind of, it's just a gray hoodie with an EVAC logo on it and so forth. I did order a few others, and so a few extra in different sizes. So not only will the people who signed up for them be able to get theirs, but if you're interested as well, there'll be extra ones on the back table as well. Let's see what else I have here. Oh, member presentations. So our first member presentation is Alice again, and she's going to talk to us a little bit about the Seestar devices.
Thank you, Steve. Let's see. All right. So I've had a lot of people ask me what the difference is between the two Seestars. And so I thought I would just do a quick little member presentation and kind of compare the two. So first question, why did I buy the thing in the first place? Well, I absolutely love taking pictures. And when I first started learning astronomy, my partner Gordon was teaching me, and he gave me a 6-inch Dobsonian. And then he gave me an iPhone adapter to put on the eyepiece. And that's how I took this picture. It was the lunar eclipse, November 2022. It came out great. I was hooked. I'm like, this is so cool. However, when I started doing the research into what is really astrophotography, I don't have the patience to sit down in front of a computer and start stacking all those pictures. Those pictures are called subs, by the way. And I didn't have the money either for doing, getting all the pieces of equipment that you need to make it happen. And one evening we were watching a YouTube video, and it was Astro Biscuit is the name of the guy. And he's over in the UK. And he was doing this little showdown on who's better, a smart telescope or an astrophotographer. Now, he didn't have a Seestar, he had a different smart telescope, but in the end, I thought it was so cool that he just put this thing up on his roof and operated it with a tablet. And then he did his thing with his astrophotography. He, of course, won. But I was fascinated that the pictures he was getting with the smart telescope were amazing. So I kind of mentioned to Gordon, I'd like to do that. And so he started doing some research. The first one that came out was the Seestar S50. So basically, this little guy has everything you need to do astrophotography, which is the telescope, the mount, the software, the camera, all the stuff that you need is in this one. Dew heater. So there's the S50, and it's $500. Next is your S30, so it's $350. So exact same thing, smaller version here. Now the only real difference will come down here to the next slide. Here are the differences. I got an aperture of 50 millimeter, a focal length of 250 millimeter for $500 on the S50. The S30, I've got an aperture of 30 millimeter, focal length of 150 millimeter. It comes with a wide angle camera, and then it's 350. So I just want to focus on the focal length. If you have, pretend you have a straw and you're looking up in the sky, and I'm going to look at a focal length of 250 millimeter. I'm going to be like right here. And what I see through that little circle is what the S50 sees. Now, if it's 150, it's going to be closer, right? And so now I'm going to see a little bit more. That's what the S30 sees. So really, the S50 is zoomed in, and the S30 has a wider view. So what did I do? I took these two Seestars, I put them out, and I looked at different objects. With the deep sky objects, I did the same amount of time. And then we did, the first thing everybody does when they get a Seestar is they look at the sun. So to your left is the S50. And what's cool is it's down here. It tells you S50, tells you where you're at. You'll see on the deep sky objects, it'll say the deep sky object, what it is, and it'll say how long the exposure is. But the S50 is on your left, the S30 is on your right. So you'll see that difference I was telling you about. Here, you've got the S50. Here, you've got the S30. Still looks good. It's not bad. Next, you always do the moon. Very detailed, very beautiful. Again, you see that zoomed in versus the wide angle. Now, the interesting thing that I found when I did this, now this is flipped. This is the only slide where it's flipped. The S30 is on that side, the S50 is on this side. So it was about civil twilight, 6:45. I put both of the telescopes out and took a picture, but you'll notice the S50 zoomed in and I have detail of the moon, but the S30, not so much. I had to wait until it got darker before it would get the detail. And then I also had to do an autofocus. So there's a little bit of a difference right there. All right, Orion Nebula. Again, you can see zoomed in on the S50, and then you get this wider view. You've got the Running Man up there on the S30. Down here is the minutes that I did for each one. And then it also tells you what M number or IC number. All right, here's the interesting one, the Horsehead Nebula. Now, I had both of these on the same object here for 2.5 hours. However, the S30 kept more of the subs or more of those 10-second exposures, where the S50 kicked out more of them. So down here it says 68 minutes for the S50, 110 minutes for the S30. I will have to say in this case, I loved the S30, that wider view and just more detail, although the S50 is beautiful as well. Guys, remember this picture because at the very end, I'm going to show you a really good picture. All right, next, the Heart Nebula. This is the mosaic mode. So if there's an object like the Heart Nebula or the Andromeda Galaxy, you can do what's called mosaic mode and it'll get it all in the picture. Now it takes a while. This one took 69 minutes. This one took 70 minutes. And as you can see, I have not altered any of these photos. It's very dim. The only thing I have done is each Seestar has what's called a AI denoising, artificial intelligence denoising. And denoising means it just takes out all the brightness and all the light pollution and fills it all in darker. But this is what you get without playing with it right here. It will also tell you how long it's going to take to do a mosaic mode. Here's the owl cluster. Again, 7 minutes, 6 minutes, but you can see that zoomed in and then the wider field of view. All right, here's M37. My man says looks like heaven. Diamonds on, what is it, velvet, black velvet. So again, beautiful, both of them, but you're just getting different views. Here's the Whirlpool Galaxy. Again, not bad. I've also noticed somebody asked me last month about the red tint that they're getting in their S30. And I'm getting that same thing. There's like a red tint to it until you denoise it. Denoising it takes away most of that red tint, but I am noticing a bit of a red tint in the S30. Here's Bode's Galaxy. Again, you can see you get a wider field of view. I've got an extra galaxy right there, but I don't have it in the S50s. All right, planets. Neither one of these is good at planets. Great at the sun, great at the moon. Here's the planets. S50 will pick up Jupiter and it'll get the I have 3 Galilean moons. The S30, I just get this white dot. I don't even get any moons. Mars, Venus is gonna look just like this, only worse. You can zoom in. There is a zoom in mode, but it's just gonna be a bigger fuzzy dot. So no planets, none at all. All right, so my closing thoughts. All right, the pros of the Seestar S50. It seems to take a more close-up view. I like that personally. It has a better tripod. I can adjust it. It sits up higher on the table. The only con I could see is it's $500. The S30, it takes a wider field of view if you're into that. It does keep more subs when it's stacking. It has that additional wide angle lens, but it's really just to help find the sun or the moon, or if you're looking at scenery. And it's $350. Cons, its tripod is pretty lame. It's non-adjustable. It sits really low on the table. And sometimes you do need to use that wide angle lens to find the sun and the moon. So which Seestar do I prefer? Personally, I prefer the S50. I just like all the little extras as far as the tripod is much better to use. I like having the object zoomed in more, just personal preference, but they're both very good. If I had a recommendation, I'd recommend spending the extra $150 and get the S50. Now, here is a Horsehead Nebula taken by one of our members, Josh, using traditional astrophotography equipment. That's what everybody's really going for. I don't have the patience for that, but I can admire it, and I think it's absolutely beautiful. But this is hours of subs and hours at a computer. So any questions? Yes. Oh, sorry, Amanda's got to get to you.
I found with the S50, I own one too. With the planets, what you need to do is kind of play with the exposure quite a bit. And if you manually change, like for Jupiter, the exposure, the moons will go away, but you can see the belts.
Okay, okay.
And you can see what looks like a little bit of detail on Mars, even though it's not really all that close to, right now it's brighter than it often is. And with Venus, you can see the phase, but you gotta cut back on the exposure. Otherwise, like you say, it's just a big fuzzy blob.
And he brings up a good point. You can change your exposure. You can do 10-second exposures, 20-second exposures, and 30-second exposures. And I've just kept it on the 10-second exposures. Yeah, yeah.
How does Seestar find the objects?
So when you first unbox the device, you hook it up to your tablet or your phone, and it'll ask, can we use your GPS coordinates? And you say, yes, you allow it. So that's how it finds where it's at, by your GPS coordinates, either on your tablet or on your phone. Right. Mm-hmm. She'll get around to you guys, I promise.
So I have a Seestar S50 and I've had it a while and I've used it. And I also have regular astrophotography equipment, and that thing is a blast. Just a couple things to add about these that make it even better. It's
Yes,
on
please.
an altazimuth mount, which means you get a lot of field rotation, but you can mount it in an equatorial mode. And like I took an hour and 45 minutes of Bode's Nebula, Bode's Galaxy, and this without any field rotation at all, and it'll stack it right on up. The other thing is it'll save all the subframes as fit files if you want. You can bring them over into Serial or over into PixInsight, and you actually get much more control of the stacking. That red is, there's a lot of processing that goes on in that S50, and they're getting rid of the horrible pea green soup light pollution by adding magenta. And so if you do a background extraction in the software, you can get rid of all of that, and it's no problem. So it's kind of a cool little thing. There's also I recommend if you get one of these, you can get a light pollution filter, like a 2-inch light pollution filter. There's a number of them you can buy. Antela makes one and some others, and put it on there. And from these kind of Bortle 7 to Bortle 9 skies that we have in urban, suburban Phoenix area, it really does a good job with it. So I recommend that you try that stuff too. You can buy a Skywatcher wedge, and then just mount that thing, just lean it right into the North Star, and it'll polar align.
Oh, wow. Yeah, it does have, it comes with its own light pollution filter in it, but I've never added one. And like I said, I don't have the patience to sit down and do all that. I'm a point and click kind of girl. Yeah.
That actually answered one of my questions, but my other question is, can you totally remove the battery so that you can pack it in your checked bag?
Yes, you can totally remove the battery.
Did you use a solar filter when you're taking a picture of the sun?
Absolutely, yes. They both come with a solar filter. The S30 has like a little magnet on its solar filter, and the S50 you have to kind of press on, but they both come with solar filters, yes. Here, in here, right there. And then up front.
I don't know much about astrophotography, but is there a way to be creative with it, or is everyone's Seestar picture of an object all the same?
You can totally be creative. There, like that gentleman in the back was saying, you can actually save every single one of your subs or your pictures, and you can download it on a computer, and you can do the traditional processing. There's also a little bit you can play with on the app itself that you can lighten and darken, and you could totally have fun. Absolutely. Anybody else? Andrew?
Yes, you can travel with the 50 and without getting any problems with customs or the security. And you can take it down to the Southern Hemisphere if you're lucky enough to do that and take pictures there. So it was, you don't have to worry about traveling. You can also, it's very lightweight, only weighs about 2 pounds, and you can fit it neatly into your baggage, and it's really, really convenient.
Yeah, it is. That's what I love about them too, is they are so portable. You know, you want to go and do some photography, just pack it away, shove it in the car and go. Anybody else?
I know, right? Bring my steps in.
What about darks, lights, not the lights, but darks, flats, those extras that in astronomy that you need to take?
I don't know what you mean.
Calibration frames.
I have no idea, because this thing does everything for you. Because I don't know what you're talking about.
Sounds like
the gentleman in the back would probably know. He's dying to answer your question.
So you'll have to shoot dark frames and flat frames separately. You know, it's automatically going to do bunch of 10-second integrations. That's, you know, you can go into advanced and do 20 and 30 seconds, but with this light pollution, 10 seconds works pretty well. And especially with bright things, you don't blow out the middle of the Orion Nebula or whatever. So you can just cover the lens and shoot 10, cover it, or you can put a flat light source in front. And really, it's only a 50 millimeter apochromatic lens. You know, with a it's just got it's so easy to put you can just put a T-shirt over that and shoot at dusk, or it really is easy. So.
Thank you, sir. Appreciate that. Anybody else? All right. Thank you, guys. There you go.
Yeah. All right. So member presentation 2, Mr. Gordon. You're on. Okay, bye.
Hello, everybody. As you can see, I'm Gordon Rosner, and we're going to talk about telescope collimation, and mostly what is it? Not how to work it, how to fix it. It's just what is it? So that if it needs to be done, well, then we'll go on to another part, not tonight, but maybe we'll do something about that. Nope. Page. Okay, here we go. And you can read that on your own, but basically what it is, collimation just means that all the optic elements are in line how they're supposed to be. That's it. Doesn't have to be all scientific, but that's the official designation up there. Okay, now this is going to be a presentation about an easy way to check collimation, not how to do it, but how to check it to see if your telescope actually needs it to be done. So how do you know if your telescope needs to be collimated? Okay, pick a star that's easy to find and focus on. A pretty nice medium to large type of star, preferably if it's straight up. Because if you have a reflecting telescope, you've got that big heavy mirror down at the bottom that moves up and down. And if it's sideways, it'll tilt over just the slightest little bit and it'll give you a false reading. So somewhere around straight up is the best way to do it. You can do it horizontally, but you're not going to get a precise look at it. And then defocus it. Now that you got that star in your eyepiece field of view, defocus it. By that, I mean just turn that focuser a little bit. What you want to do is make that star into a donut with a black hole in the middle. Now, what I'm talking about here is Newtonian telescopes. That's Dobsonian telescopes, Maxutovs, Cassegrains, those that have a secondary mirror inside of it that's blocking some of the view. That's what we'll be concentrating on tonight. So that donut shows up, and here's what the star would actually look like. Now look at those rings that just showed up. That's what we're interested in. They're called diffraction rings. And what I have here, I always like to hand stuff out for people to touch and hold and look at. Now these aren't diffraction rings, they're called Newtonian rings. But this gives you an idea of what you're going to see. Here's kind of a donut in the middle, and then it's got the refraction rings around it. So pass this around. I got this when I was in the Army, and I still have it after over 50 years. So hopefully I'll get that back tonight. So you can say, hey, you can do this inside during the day by creating an artificial star. And that's what I have back there. There's a flashlight, that's my artificial star, and then my telescope over there, which is focused on that artificial star, but has been defocused a little bit. So that's what you're looking for. When you have your telescope, you're looking first, get that thing in focus, and then defocus it a little bit to get that donut, just like what's inside that telescope eyepiece over there. So look at the diffraction rings. Those rings around it are the important things. Sometimes you'll get a black blob in the middle, and that's just because of that secondary mirror, the holder for it. That's really not important. What you want is the diffraction rings being nice and concentric. In fact, if you got good eyes, you can look right in the middle and you can see a little dot. And that little dot is part of the optics. But that black part, some telescopes purposely move that secondary mirror over a little bit. So you're going to see that holder not centered. That's fine, no problem at all. Actually the rings is what you're looking for. So see when it's focused, and then here's defocused, which is kind of that donut, the dark area in the middle. Now bad collimation, look at this. This can be what you see because the sky is turbulent. Especially an open tube like a Schmidt-Cassegrain, or not Schmidt-Cassegrain, a Newtonian that has an open end to it, like that white one, little white one over there. So what's happening is there's air currents inside there that's making it flicker around a little bit. Plus the sky, the turbulence in the sky is making it flicker. It's just like looking through a swimming pool, the water in a swimming pool, how it's dancing around on the bottom. Same thing with the sky. So here's bad collimation. See the way it's pushed off to one side? So the optics are not lined up well. They're lined up well, they're off. Okay, here's what you more likely will actually see this flickering that's going on. And then down here, yuck. So see the way that that dark donut hole is shifted off to the side? That means that you're out of calibration. Now, if you're only out a little bit, like most telescopes, commercial ones, yeah, they're pretty good, but they might be a little bit. If it's just the tiniest little bit, forget it. Don't mess with it because there's 11 screws that do different things in there. So it's better, unless it's really out, just leave it alone. So yuck. You just found out your scope is a little out of calibration. You may not have even realized it. Now over there, that telescope that I have an artificial star set up. There's a little flashlight over there with a hole in it, just like this. You see that little hole in it? I just made an artificial star. So the telescope is lined up with that artificial star and it's defocused a little bit. So go ahead during the break is look through it and see the way you can see the donut. If it was in focus, it would just be a little point of light. But see if you can see that donut. Is this in collimation? No, good. Hey, you've been listening. Great. Okay, out of collimation will affect visual and your photography, both, because the optics just aren't lined up. And sometimes it can be kind of obvious, like if you're dull like that, you know, kind of fuzzy, well, maybe you're out of collimation. Should be nice and sharp like this. Okay, nice clear pictures you just showed, but I have a turbulent sky above me. Defocused stars fuzzy and jumping all around. It looks like that. I can't even see the donut. Well, I said that we have a solution for that. You said I could do this inside during the day. Yeah, it's easy. Just create an artificial star. And during the break, walk on over there. Look, you can see I have my artificial star, my flashlight with a little bitty hole in it over there, and the telescope is lined up on it. I just made an artificial star. Yeah, it's easy. There it is. You just take a flashlight. It doesn't have to be a bright one, a medium-sized one. You got to be able to see it. Nicely wrap aluminum foil over it. Kind of tight, but get it nicely over there. Using a small pin, the smaller the pin, the better. Remember, stars are just points of light. They're just different brightnesses as we see them. So you want the smallest little light pinhole in there, just like this one right here. There's my artificial star. And then see the light shining through the tiny hole? Right? You just made an artificial star that you can look at during the day. Plus, you don't have the difference in temperatures in your house. You don't have you're not looking through an entire atmosphere of dirt and wind and turbulence up there. It's not as good as looking at a real star, but it is awfully close to being the same. Okay, now place that artificial star on the table, boxes, something, whatever it is, kind of horizontal. I mean, we have to do horizontal. We can't be having it pointed up. It's got to be at least 20 or 30 feet away. Kind of the further away, the better. But what do we got here? Maybe 30, 40 feet, maybe 50. It's working just fine. Now center your scope on your artificial star and do the exact same process. Is that donut right in the middle? Is it off just a little tiny little bit, or is it way off at the side? If it's right in the middle, leave it alone. If it's just a little tiny bit off, leave it alone. But if it's way off, then you got to do something about it. So I just found out my scope is out of collimation. What do I do? It's always something, you know, with these telescopes, it's always something. So don't get upset. Hey, East Valley Astronomy Club President Steve Bradshaw, take it away. What happens if you guys now look for an artificial star or maybe a real star and find out that donut is pushed over to the side? The little rings are not lined up, right? What do you do? Steve is going to tell us.
The solution's easy. You just go to Gordon, you pay him $50, he does it for you. So anyway, oh, here. Don't forget your artificial star. Okay, so anyway, yeah. So anyway, actually the indoor star works pretty good. I had a mount issue on my telescope over the summer, last summer, and so I took it down to Star Arizona in Tucson, and so he fixed the mount. It was actually pretty involved. I mean, literally had to disassemble the entire mount to get to the problem. But anyway, he said, "Hey, while you're here, no charge. Did you bring your optical tube with you?" And I said, "Sure." So he set it up, and he actually collimated my my optical tube for me, actually, as just as a nicety. And what he uses is he has at the very back of his shop, he's got this little box hanging on the wall where he has a little fiber optic cable sticking out, and he's got a little point of light coming out that fiber optic cable. So your flashlight reminded me of his little fiber optic cable. Anyway, one of the things that the club leadership has been talked about in the last, couple of meetings for the board and so forth is wondering if you folks would benefit or enjoy having a collimation class, sort of a hands-on collimation class where you can bring your scope in and learn to collimate the thing. So, and the big thing would just be decide, well, do we want to set it up for like a Friday club meeting? So, from 6 to 7, we collimate telescopes, and then 7 we have the meeting, or would we want like a Saturday afternoon, for an hour in Saturday afternoon kind of thing? So we haven't decided that, but the biggest step is who would benefit from having a collimation class? Would you like to have a hands-on collimation class, or everybody's pretty comfortable with it and you don't really need it? So we're this is a poll. Raise your hand if that would be useful to you, and if not, we'll skip it. So just a few, looks like we're going to skip. So anyway, just a few. So anyway, okay. But anyway, so thank you, Gordon, for that. We appreciate that. And like I said, it was just a good way to kind of test the waters with the club as well. We're trying to figure out what you folks want. So if you have ideas about what you'd like to do, what you'd like to see, what you'd like to hear, where you'd like to go, whatever else, please let me or Amanda, our vice president, or Jeff, our secretary, or anybody you see kind of wandering around looking like they're official, then tell them, and they'll bring it back to the board, and we'll discuss it during a board meeting and all that. So anyway, and we do have some good fun stuff coming up. We did have, we've actually been discussing this for a month or so now. We're actually, and I'll have more details next month during the meeting, but we've actually have set up a tour of the MIR lab down in Tucson. So we'll be talking to you folks about that at the next meeting in April. And we'll go down there. We're talking about taking a shuttle bus down, so you don't have to drive. You can just sit on the bus, let somebody else do the driving, chit chat on the way. And we'll go down with tour of the MIR lab. If you're not familiar with the MIR lab is, it's where they make telescope mirrors. And it's actually under the stadium at the University of Arizona in Tucson. And so you actually go underneath, and we're not talking like 6-inch mirrors or 8-inch mirrors or 10-inch mirrors. We're talking like 26-foot diameter mirrors. These are like for professional mirrors for professional telescopes that are going to go in large observatories somewhere. In addition to that, they don't normally tour this place, but there's another place down there called the Space Imagery Center, and we're going to have that as part of the tour as well. And they've been collecting space photos and imagery for NASA since back like in the Apollo days. And so they're going to open that up to us and allow us talk a little bit about what's going on there, and then actually turn us loose and let us look at all the photos and stuff for a while as well. So anyway, we'll talk more about that next April in our April meeting, and you'll hear more about that as we go along. Anyway, we are on our break.
All right, if you guys are ready, please take your seats. Our featured speaker tonight is going to be Dr. David Williams. He is currently the co-investigator and deputy lead for the multispectral imager on the NASA PSYCHE mission. So please welcome Dr. Williams.
Thank you. Thank you very much. It's a pleasure to be back here. Before the meeting, I was looking through my record of my public outreach presentations going back to 2014, and I realized that the very first public talk I recorded when I started keeping track of them was actually to your group when you were still meeting at Scottsdale Community College in January of 2004, which was just after the Spirit Mars exploration rover landed to talk about Mars stuff. So it's great to be back. And yes, I am a member of the science team. I'm the deputy imager lead for the PSYCHE mission. I've worked on quite a bit of different planetary missions throughout the solar system. But today I want to give you an update on how our mission called PSYCHE is going. And let's see here. I guess I have to do it right here. All right. I usually like to start my talks with sort of a back out to the universal view and talk a little bit about why we choose to explore space. And I can go through this pretty quickly because you guys, being amateur astronomers, and maybe some of you who have been professionals, really know about all of these kinds of justifications. But as you can see in this list here, the reasons why we choose to explore space, scientists like me do it for the science, to understand the cosmos, how did the universe form. But there's a wide variety of reasons that we choose to explore space. We do it for national prestige because great nations undertake great things. We do it for national security reasons, maintain the high ground, protect from adversaries. We do it for economic reasons, to identify and exploit space resources, to enhance national economies. We do it for sustainability, to develop the technologies to better preserve the Earth and its citizens. We do it for the educational reasons, to inspire the next generation of scientists and engineers. And then finally, we do it for survivability, because the reason why the dinosaurs aren't here is because they did not have a space program. They could not detect and deflect the asteroid that hit the Earth 65 million years ago that wiped them out. So the way that we can protect ourselves is to transform humanity into a multi-planet species. So what is NASA's role in exploration? Well, when you think of NASA, you may think of the Apollo program or the space shuttle or the International Space Station, usually the human-related activities. But NASA is actually much bigger than that. It has 5 mission directorates, as you can see listed there, 2 of which are focused on human spaceflight activities. Space operations does the low Earth orbit and the space station stuff. And Exploration Systems Development Mission Directorate, they're the ones who are working on the Artemis to send humans back to the moon and then eventually onto Mars. And then there's one called the Science Mission Directorate. So when you have somebody come to talk to you about astrophysics or planetary science or something like that, we're all funded from the Science Mission Directorate. And it's actually split into 5 different divisions. Heliophysics studies the sun, Earth science studies the Earth, planetary science studies everything in the solar system except for the sun and the Earth, astrophysics studies everything outside the solar system, and then the one at the bottom is a cross-cutting that covers all of the divisions focused on biological and physical sciences research. So with that, now let's talk very briefly about how we explore the solar system, starting with telescopes first, because that's how we discover things, but then we go to robotic spacecraft leading to human missions. And it may seem a bit haphazard because you hear about flybys to one body, orbiters to another, rovers on yet a third, but there's actually a very thoughtful way that we think about exploring the solar system through this phased approach of doing what's technically possible, what we have the engineering skills to do and build, what's affordable, what Congress will give us the money to do, accomplish the easy missions first successfully, and then go on to the more complex missions. And you can see in this list over here, those are the order of the different types of missions in order of increasing cost and complexity. So the easiest is a planetary flyby, launch a spacecraft, it flies by a planetary object, takes pictures, collects data, transmits it back. That's how we get our initial reconnaissance, our initial understanding of what a planetary object is like. Then, of course, we want to do an orbiter, something that can slow down and get into orbit, and as the planet rotates around it, the spacecraft gets a global data set. You get your global assessment of an object from an orbiter mission. And of course, once you know about it from orbit, then you want to get down to the ground. So you want to send a lander. There's different ways you can land. Hard landers, take pictures as you get closer and closer, and then they smack into the ground, and all the instruments are broken. So they're of limited use. We much prefer soft landers that actually have parachutes, retro rockets, airbags, something to slow down so you can land on the surface. You can make in situ measurements right there and get those wonderful 360-degree panoramas of your landing site. But as what normally happens when you do that, you see something interesting over there, and you wish you could travel to it. So that's where you need mobility on the surface, and that's where rovers come in, which can either walk or drive or crawl, or if it's an object that has an atmosphere like Mars or Venus or Saturn's moon Titan, maybe it can fly or float through the atmosphere to give you your mobility to study different locations on the surface. The next hardest and complex thing to do is called robotic sample return, where you collect a sample of rock or dust or ice or atmosphere, put it into a container, launch it back from that object. It lands here on Earth, where we can study it in our laboratories, like the ones we have at ASU, where you stick in little pieces of some material and you get all this wonderful compositional and mechanical and isotopic data. And then, of course, the hardest thing to do, the most expensive thing to do, are human missions, crewed missions for humans to orbit and land on a planetary body. So here's the status of solar system exploration as you see right now. And you can see I put on here the different modes of exploration across the top on this chart, and then the major objects of our solar system, starting with the planet Mercury closest to the sun, all the way out to Pluto and the Kuiper Belt. So you see the column for telescopic observation is all filled in because that's how we discover these objects. You see the column for flybys is all filled in, starting with the Mariner 2 flyby of Venus in 1962 and concluding with the New Horizons flyby of Pluto in 2015, and it actually visited a Kuiper Belt object, Arrokoth, in January of 2019. So we have completed the initial reconnaissance of the solar system led by NASA missions. Now, as you move across the chart here, from orbiters to landers to rovers, et cetera, you see it's less well filled in. Where it is filled in is for things closest to Earth. So orbiters on most of the rocky bodies and a lot of the small bodies in the asteroid belt, some comets. As you move to the outer solar system there's still a lot that hasn't been explored. By the way, the colors on here, white are old missions, green and blue are missions that have been funded, are operational, that are in flight. Things that are in yellow or red are things that have been discussed, things that are in different stages of development. Maybe they haven't been fully funded by Congress. So as you see here, the only place humans have been, of course, is the moon. But what we'd like to do is to completely fill in this chart, completely explore the solar system, and then we will be able to boldly go where no one has gone before, as they say in my favorite TV show. So with that preamble, now let's get to PSYCHE. So what I'd like to do in this talk is basically review a little bit about asteroids. What are they, where are they located, and why we care about an asteroid named PSYCHE, and tell you about our ASU-led PSYCHE mission, its objectives, its instruments. It did launch back in 2023, and how it's going right now as we cruise through the solar system, what we expect to find, and a little bit about some of the other asteroid missions in flight, leading to conclusions and a look ahead for Q&A. So, asteroids, what are they? Small bodies, minor planets, protoplanets, usually with diameters less than 500 kilometers. They look, they're very irregularly shaped, mostly composed of silicate rock, dust. Maybe they have volatiles, and in this context, volatiles means ices, probably water ice. So you see there's a picture of 21 Lutetia, is imaged by the European Space Agency Rosetta mission. You see very lumpy, very irregular impact craters, maybe other things on the surface. Where are most asteroids located? Well, most of them are in the main belt between the orbits of Mars and Jupiter. There's a population at the Lagrange points, the L4, L5 Lagrange points of Jupiter, called the Trojan asteroids, and we have a mission in flight there. The Centaurs occur between Jupiter and Neptune. And then, of course, the ones that you hear about probably the most are the near-Earth asteroids, the ones whose orbits come to or cross those of Earth and the other inner planets. Those are the potentially hazardous ones, and there's about 4,700 of those that have been identified thus far. So any of these type of flybys, they occur quite often. A lot of material burns up in the atmosphere. Sometimes you have fun things happen, like Oumuamua, the extra galactic object that came through back a few years ago. But we will talk about PSYCHE here in this talk here. So most of what we know about asteroids comes from the reflected light spectra from telescopes. And we also know a lot about them from meteorites because most meteorites are pieces of asteroids. So we are able to classify asteroids based on their telescopic spectra. C-type is the largest class, carbonaceous rich, carbon minerals in it. S-type for stony. D and P, dark and primitive, those are the Trojan asteroids. V-type is Vesta, which was the target of the Dawn mission, which I worked on last decade. And then you have M-type. And in this case, M stands for metallic. We think they're the iron nickel cores of asteroid parent bodies. Anyway, for all these different classes, what we've determined is that asteroids are basically the rocky remnants left over from the formation of the solar system. The ones that occur in the main belt are at a location where they just could not form a planet. The gravitational power of Jupiter is just so great, it disrupted that particular location of the solar system and prevented a planet from forming there. So here's a chart about the spacecraft exploration of asteroids. And the ones in bold on this chart were actually missions that were dedicated to going to asteroids. The ones that are not bold are where the primary target of the mission was someplace else in the solar system, and it just happened to fly by an asteroid to collect some data. I was actually there working on the Galileo Jupiter mission during the Venus Earth Moon cruise phase of the early 1990s. So I was there when we got our first images of 951 Gaspra and 243 Ida. It wasn't until the year 2000, just 25 years ago, the first asteroid dedicated mission visited asteroid 433 Eros. And then since then, you see there's a little bit more bolder things in there. There have been a lot more asteroid dedicated missions, including the sample returns from asteroids with Hayabusa 1, Hayabusa 2, OSIRIS-REx. We visited the two big objects of the main belt with the Dawn mission last decade, asteroid 4 Vesta and number 1 Ceres, which now, of course, is reclassified as a dwarf planet. And then in green in the bottom are the two active asteroid missions in flight, Lucy and Psyche. So here's one of my favorite graphics. Emily Lakdawala of the Planetary Society made this back, I think, in 2010 or 11. So this is all of the asteroids and comets that were visited by spacecraft prior to the Dawn spacecraft arrival at Vesta in July of 2011. And it just gives you a good view of what asteroids look like. Once again, they're regularly shaped, heavily cratered. You might be able to make out other features on the surface like boulders. I can see some boulders on here. You see these lineaments in here. Maybe they've been affected by some sort of planetary process. But, giant rocks in space. And as I said, they may or may not have volatiles. Certainly comets, dirty ice balls or icy dirt balls, whichever we like, will definitely have a lot more of that type of material. So when we think about asteroids in context of the planets, though, they're much, much smaller. And the implication is they've had less internal heat and less geologic planetary processes acting on them. So here you see Mars, Mercury, the Earth's moon in the same size scale to dwarf planet Ceres and asteroid Vesta. So you see much, much smaller objects down there. Now let's talk a little bit about Psyche, and I'll show you how it relates to that in terms of size. So why do we care about asteroid Psyche? Well, first of all, it's 16 Psyche. It was the 16th asteroid discovered by Annibale de Gasperis of Naples Observatory in March of 1852. You can see from these telescopic shape models there that it's roughly elliptical, shaped like a potato, 279 by 232 by 189 kilometers in size. This is actually the largest of the M-type asteroids, the largest of the metallic asteroids. It orbits at 2.9 AU. It takes about 5 years to orbit the sun once, but it rotates fairly fast, in about 4 hours. So we think that the M-type asteroids are perhaps the cores of some of the asteroidal parent bodies. Just like the Earth has an iron nickel core, we think that at least some of these M-class asteroids may be something like that. And that's part of the motivating reason for the Psyche mission, is to go out and investigate this type of asteroid that's never been visited by a spacecraft before and try and determine its origins. So if it's a iron nickel core from an asteroid parent body, then maybe the corresponding meteorite that corresponds to that would be one or more of the families of the iron nickel meteorites. You have all seen probably iron meteorites. You've seen the wonderful pallasites, probably at gem and mineral shows. But there's a whole sets of families of these. And it would be nice if we would be able to relate if whether 16 Psyche and one of these iron meteorite families are actually related in some way. That'll be a stretch, but we will see what we can determine from that. So I just give you some information here about the density of Psyche. It's solid body, but it appears to be fractured, maybe has some porosity. There could be carbonaceous material on the surface, certainly some silicate material, maybe even water ice in permanently shadowed regions, just like we see at the poles of the moon and Mercury. We will find this out as part of the mission. How big is asteroid 16 Psyche compared to the others? Well, here's Vesta, which is the size of the state of Arizona, if you just sat it down on the surface. And there you see Lutetia, which was the big one in that first graphic. So Psyche is in between the two. So there's where you would have Psyche in the size comparison. So what does that mean physically? Well, that Psyche is the size of the distance between Phoenix and Flagstaff, or the state of Massachusetts if you leave off Cape Cod. So that gives you an estimate of just how big this particular asteroid is. So when you develop a planetary mission to investigate an object in the solar system, you usually need to have a driving question that then motivates your scientific objectives, because we don't just go for the sake of going, we have scientific questions that we want to have answered. So for the Psyche mission, the driving question is asteroid 16 Psyche the core of an asteroid parent body? And to determine that driving question, we have specific objectives, questions that we're asking. Is Psyche a planetary core, or did it never undergo melting? Is it a piece of unmelted metal from the beginning of the solar system? What are the relative ages on its surface? Do small metal bodies incorporate light elements expected the same way that the Earth's core does? Did Psyche form under more oxidizing, reducing conditions relative to the Earth's core? And then what is the topography of this world? So you see here on this graphic, once again, the shape of it. You see, even if it's a potato shape, it's not smooth. There's indentations on it. Now, those are most likely impact craters. So we know that this has been affected at least by impact cratering. So with these driving questions, we want to relate this back to the theory of the formation of the solar system. So you'll remember the solar system formed out of a gas cloud that was rotating and condensing. The sun formed in the middle. The gas and the dust was impacting each other to gradually form dust particles that became cobbles, that became boulders, that became planetismals, and that eventually became the inner planets. So in some cases there, some of these probably impacted each other and maybe broke apart. And what we think happened with Psyche is that it was a molten iron nickel core of one of these planetismals that was hit by one or more hit and run impacts. Basically something that knocked off most of the crust and mantle. So you had this molten iron spinning core. It would have developed a magnetic field. It would have crystallized probably from the outside in. It would have separated out any sulfur materials, because sulfur and iron metal are immiscible. That means they're going to naturally separate. You might add sulfur flows on the surface. As the thing cooled and crystallized, it would have locked in the magnetization there, and then subsequently hit by impact. So this sequence here is one possible sequence for how this asteroid formed. This is one of the things that we want to test. So how big is a spacecraft? So we built a spacecraft to go there, and here's a graphic. You see a person on there, looks like an Earth orbiting satellite, because the company that we worked with to build this actually builds Earth orbiting satellites. And you see it's got all the necessary parts to it here. You got to have a high gain antenna to communicate with Earth. You've got to have an interior that has computers and avionics and all that type of good stuff here. We have this jungle gym that holds a couple of the instruments, magnetometers on one side, gamma ray and neutron spectrometer on the other. You got to be able to take pictures. So here's where our cameras are on that side of it there. And of course, you have to have a couple of methods of propulsion. We have cold gas thrusters, and we have solar electric ion propulsion, similar to what the Dawn mission used to go to Vesta and Ceres. The solar panels are on the sides. And when you deploy the solar panels, you see there's the guy there. It's about the size of a tennis court. That's how big it is once the panels are deployed. So how long did it take to develop this whole thing from beginning to where we're at right now? Well, the leader of this mission, Professor Linda Elkins-Tanton at ASU, she had her first discussion with folks at NASA's Jet Propulsion Laboratory in Pasadena, California, going all the way back to 2011. Concept about how to do a mission to this object. NASA put out an announcement of opportunity, which is a proposal for new missions back in 2014, and we submitted one to do this mission. And there were about 25 different mission concepts that were proposed, and NASA down selected to, I think, maybe 4. And then they gave us all these 4 teams $1 million and said, develop and refine your mission concept. So we did that. We submitted that proposal in 2015. And let's see, put the rest of it here. We found out of the proposals that were selected, they selected 2, our sister mission Lucy and Psyche, and we found out in January of 2017. So we were selected at that time. And since January of 2017 up until our launch in October of 2023, that was our development phase. So it took about 6 years total to do that. So here you see where we are now in 2025 after cruising for over a year. So the spacecraft body was built by Maxar Technologies, as they've built a lot of satellites in Earth orbit that use this special solar electric ion propulsion. The instruments were built at different institutions I'll talk about. Here you see we've actually completed construction on the spacecraft. This is in the clean room at NASA's Jet Propulsion Laboratory. So that's me, and there's a spacecraft behind it. These thing on the side, that's where the solar panels would attach. And you can see the jungle gym, that's where the instruments would go. And then on this face here, the multispectral imagers are these 2 silver things that are sticking up right over there. So the spacecraft was completed on time. However, we did not meet, it was shipped to the Cape in April, Cape Canaveral, Florida, Kennedy Space Center in April of 2022. It was supposed to be for an August launch. However, one thing was not quite ready. The guidance, navigation, and control software that was developed for the spacecraft was developed, but it was not fully tested in time to meet the launch window. So NASA decided, well, you're not going to launch a spacecraft unless all systems are ready. So they basically gave us a 1-year launch delay. So we did do the testing in that 1-year time frame. Everything was working right. So that's when we just basically continued to get everything ready to go. Here's another view of the spacecraft here. You see the high gain antenna over here. This thing over here is the DSOC, the Deep Space Optical Communications. It's a test. It's not actually for studying Psyche, but it's a test demo. And the idea is you use a laser that you can shoot out of that, and it hits at Mount Palomar in California, and you can transmit information through the laser beam. And Mount Palomar does the same thing, can shoot it up to the spacecraft. This technology has been tested before from Earth to Earth orbit and from Earth to the moon, but we wanted to see if the technology would work Earth out to the asteroid belt. So, and it has been working very well as I'll mention. So that takes us to launch week. So October of 2023, the science team gathered at the Kennedy Space Center in Florida, and we're doing a lot of outreach activities there to people who are visiting the Kennedy Space Center that week, handing out all sorts of free swag and stuff like that. We went out to the launch pad. So you see here the rocket on its gantry right here. This is a SpaceX Falcon Heavy rocket right here. The 2 solid boosters are a bit scorched because they've been reused. We were actually the 3rd usage of those rocket boosters on this rocket. So you see myself with Professor Jim Bell, who's the imager lead, Dr. Linda Elkins-Tanton, the PI of the mission, and some of our staff out there giving the Sun Devil, a fork there. So yeah, we got to go out and see the spacecraft before it launched the next day. And here you see basically pictures of the launch. And I have the volume turned down here, but on the right here is the actual launch. My wife took this video. They say if it's your first rocket launch, you don't actually want to be diverted in your attention. So my wife said, you watch it live and I'll try and record it. Of course, she was trying to watch it live too. So you see it goes off, the camera gets off pointed there. So it disappears into the clouds, and but it reappeared, and it was a picture perfect launch. So Friday the 13th may have been a very bad day for the Knights Templar back in 1307, but it was a very good luck day for us in 2023, and our mission launched successfully. So this is a video of the highlights there, and basically it's a much better view of the whole launch sequence. It's always good to see a good rocket launch every once in a while, particularly if it's your first time seeing one live. Because in all my years in the business, which is 35 years now, I had never been to a rocket launch until this mission that I helped develop here. So liftoff, as I said, was picture perfect. The separation of the boosters. And when you're at the Kennedy Space Center and the boosters turn back to the Space Center, you actually hear the double sonic boom when they come back down and land. And you can see that here. See, both boosters landed back at the Kennedy Space Center. So a wonderful new era that we live in now. So the spacecraft boosted out of Earth orbit, and here you see the final separation from the launch rocket here, sending the spacecraft out on its journey. I had to wait until the evening. This all occurred in the morning, and I had to wait until the evening when the imager team got together for dinner down there at Port Canaveral. And Jim Bell, I asked him, all right, did the solar panels deploy okay? And he said, oh yeah, we heard from the spacecraft, solar panels deployed, it's on its way, no problem. So that was good. That was the last thing that we had to worry about there. So here's how the mission is going to work. So you see our launch right here, October of 2023. The solar electric ion propulsion is a low mass fuel propulsion system that instead of using a chemical rocket where you burn a lot of fuel, a lot of mass, and you go directly to your target, we actually spiral around the sun as we move outward in the solar system. So the advantage is that the fuel takes up less mass, which means the mission takes up less cost, but it takes longer to get where you're going. But that's a price you're willing to pay because this mission would have been too expensive if we tried to launch on a chemical rocket. So the blue dots are when we're testing the DSOC, and you see we've been testing it here. We go out and we're gonna in the main belt, and we're coming back in May of 2026. So just over a year from now, we'll do a Mars gravity assist. It'll give us a momentum boost. They'll take us out there to rendezvous with the PSYCHE asteroid in August of 2029. So we've got a long ways to go. And then we have down here these different orbit phases here, which I'll talk about. That's going to be our nominal mission when we gather all of the science data. Let's flip it here. So this is just something about the solar electric ion propulsion. We're using a type of propulsion called Hall thrusters. It's different from what we used on the Dawn mission when we went to Best in Series, but the principle is still the same. You have the solar panels generate electricity. You have xenon, a low mass fuel on board. An electric field is applied. You ionize the xenon. You have it's impelled out the spacecraft to give you thrust that slowly builds up by firing this over weeks to months at a time. That gives you the delta V to get where you're going. So, and it's been working just fine. So there's Maxar with all their Earth orbiting satellites that use this type of propulsion system. So when we get to the asteroid, we're going to do different orbits. You start out doing a distant orbit to get sort of your broad global view, and then you move into closer orbits. Each one is optimized for a particular set of instruments. For example, the gamma ray and neutron spectrometer, which has the lowest resolution, needs to be the closest to get the best data. So they're the main thing that's happening during orbit D. Because of the launch delay, we've had to split orbit B into two parts because when we get there, only the equatorial region and the southern polar region will be lit up by the sun. So after we're going to do it A, B1, C, and D, and then back to B2, which is when the North Pole will be lit. So over the course of the mission, we'll get the whole place lit up by sunlight. So we'll get a full global view. That's basically what this says. So the best resolution we'll get is about 35 meters per pixel in orbit A, as good as 4 meters per pixel in orbit D. So what instruments are on board the spacecraft? Well, actually, we only have 3 distinct instruments. So we have cameras, we have magnetometers, and we have a gamma ray neutron spectrometer. So the imager is led by ASU, built by Mainland Space Science Systems in San Diego. There's 2 of them for redundancy. They are basically going to point down and take pictures of the surface. You look at a broadband clear filter for you to get albedo or brightness and the morphology or shape of the surface. And we also have 7 color filters that are optimized for silicate and sulfide minerals found in association with metals. That'll give us a little bit of information about the composition. And when you fly over the object and you look down on different orbits at different look angles, you're going to get these different views that you can process in a computer and make a topographic map of the surface. It's called stereophotogrammetry. So we'll be doing that. The magnetometers, that investigation is led by the Massachusetts Institute of Technology. The magnetometers were built by the Danish Technical University, which is north of Copenhagen. And there's 2 of them on a boom that measure magnetic field to a sensitivity of 0.1 nanotesla, which I guess is very, very good. These are dual flux gate magnetometers that are on the boom. And then the gamma ray and neutron spectrometer is led by the Applied Physics Lab at Johns Hopkins University in Maryland. Gamma ray spectrometers measure elemental abundance, so the amounts of iron and nickel and silicon and potassium and thorium, all those wonderful things will be measured by that instrument. Its corresponding part, the neutron spectrometer, measures hydrogen abundance. So if there is any water, ice, or hydroxyl on the surface, that instrument will detect that. And then finally, by using the communications antenna as an instrument, we can get a gravity signature. Yes, the idea is that when you communicate between Earth and the spacecraft, as the spacecraft orbits a more massive section of the asteroid, it'll pull it down slightly. And when it's over less massive stuff, it'll go up slightly. You can measure those differences in orbit very precisely with the communication system, and that allows you to determine a gravity map, distribution of mass in the interior. So if this is not a metal core, if it actually does still have a mantle and a core on it, we will be able to detect that. Okay, this is just showing you the wavelengths here of the filter wheel that's on the multispectral imagers. As I said, oldamide sulfide is a mineral that's found with metals, and then the others looking for olivine and pyroxene, things you would find in the silicates there. So since this is a mapping mission, basically with each orbit, you can put your footprints out on the surface of the object as you orbit, and you'll just basically paint the surface with images at these various resolutions. And that'll allow us to determine the geology, the topography, very, very precisely. And this is just saying in words what I just said about the gravity model. We'll be able to determine if there is any mass distribution on the object. So here's a graphic, a cartoon that my colleague Eric Gasfog made, who studies impact processes, the concept of a hit and run collision. So if you had a massive object that struck another planetesimal, it might knock off the crust and mantle. It might knock off pieces of the core. Maybe that is what PSYCHE is. As I said, this is one possibility of what this asteroid could be. Here's the artwork that artist Peter Rubin made of the asteroid based on the existing telescopic shape model as it was in 2016. And you can see a cratered body there. But this looks like a metal core exposed in space. And this is what we thought at the time when we started development of the mission. And we want to determine, is PSYCHE a metal core? Is it something that crystallized from the inside out or the outside in? Could it be a bunch of metallic fragments that just held together like rubble pile asteroids like Bennu that was visited by OSIRIS-REx? Or is it just a piece of unmelted metal left over from the history of the solar system? There's ways that you can investigate those possibilities. Here is a more recent concept. Obviously, during the mission development phase, our planetary astronomer friends have been pointing their telescopes at this asteroid, gathering more data about it. And so these are a couple of different ideas about what it could be. On the left, you see a metal asteroid, but with a lot of silicate gunk covering the surface. And on the right, you see something, an asteroid where the metal and the silicate are more intimately mixed, like you might expect in maybe a palisade. These are also possibilities about what this asteroid could be composed of. So how do you start to figure this out? Well, there's no one piece of information that will solve the problem. You basically have to take information from all of the different instruments and look at it. We'll need to have something about how does it appear in the imagers? Are there indications of sulfide minerals from the imagers? What is the nickel content from the gamma ray spectrometer? What is the nature of the magnetic field, if it has one, on that? And that allows you to start to eliminate possibilities or reduce the possibilities about what this thing could be. Here's another way to visualize that. You ask your big question, what information do you need from the magnetometer? What information do you need from the gamma ray spectrometer? And that can help push you along different lines. What you see in the actual images will also very much inform us about the possibilities of what this asteroid could be. Now, for me, as a planetary geologist, I'm very interested in understanding what geologic features look like on a world that could potentially be made out of metal. Here's an example from the Ames vertical gun where you did a hypervelocity impact experiment. So you shoot a metal ball in a metal ingot and look at the impact crater that formed. It actually freezes the ejecta partially as it's ejected out there. So it's possible that there could be craters that have these preserved metal rims on the edges of it. What would metallic regolith be like? Because we see regoliths on all of the airless bodies in the solar system to one degree or another. You have very finely grained materials on the surface of the moon, but on asteroid Bennu, we saw it was just basically big chunks of rock there. So, you know, it's a very open question what it would look like. Could the surface be made out of palisade? You know, could that have some effect on what it might appear to be? So that's the thinking that went in as we launched. And now we are in what is called the cruise phase. Until we get there, every few months, we turn on the instruments and we collect data and make sure that the instruments are working right. So here is, this is from July of 2024, this periodic maintenance and calibration. Here are pictures from our cameras. This is the wishing well cluster. So I'm sure you guys have probably looked at this with your telescopes there. But our cameras are doing a good job and they seem to be working just well. This one is from January. And here we are looking at Jupiter. And if you go and zoom in on it, we actually are able to see the Galilean satellites. Yeah, they're very, very small, but Io, Europa, Ganymede, and Callisto all were able to appear on there. So we will continue to do these things over the next few years. As we gather the images, we put them in and we use them to help develop our calibration pipeline. You guys talked earlier about dark fields and flat fields and all that type of stuff. All those things are important to us too, so that when we actually get to 16 Psyche, we'll be able to start taking images, we'll be able to process that and have information-rich images to help us study the surface. So let me just talk about a couple of other missions really quick. I'm sure you all heard about the press conference about a month ago with the results from the sample return from the OSIRIS-REx mission from near-Earth carbonaceous asteroid Bennu, and the fact that from that rubble pile asteroid, analyzing those samples that have been returned to Earth, you have minerals that are indicative of hydrothermal alteration, and you find that they contain the sources of amino acids. All of the nucleobases found in DNA were found in this. So isn't that amazing? The fact that whatever the parent body of Bennu was, these processes were going on at the beginning of the solar system. Maybe not life, but the production of the materials required for life was present at such an early point in the history of the solar system. So these samples will continue to be studied for a long time. And there's the sample return before they got all the stuff out of it. And there you see Bennu, that rubble pile asteroid, looks like a giant diamond. So the Lucy mission is our sister mission. It launched in 2021. My colleagues, Professors Phil Christensen and Jim Bell in my department at ASU are co-eyes on this mission. And this mission is doing multiple flybys of the Trojan asteroid. So they're going to be studying both camps. There's 60 degrees in front of and behind Jupiter, and Jupiter's orbit around the sun. And they're going to be investigating asteroids at both camps there. DNP, dark and primitive. So this is also terra incognita, as it were, because these asteroids haven't been seen up close. Matter of fact, this month of April, what's coming up is not a Trojan asteroid, but they're going to do a main belt asteroid flyby of asteroid Donald Johanson. That's coming up in just a few weeks from now. So you can keep an eye out for that in the news. So when you talk about asteroids, the subject of asteroid mining comes up. Now it's foregone conclusion that asteroids will probably contain valuable resources that will help us build a spacefaring civilization. Our PI, Linda Elkins-Tanton, did a calculation based on the size of asteroid 16 Psyche and the assumption that it would be made out of materials like Earth's core, mostly iron and nickel. And if you just use the size alone as a basis for that, she determined that asteroid 16 Psyche would have metals valued at 100,000 times the gross national product of all nations on Earth, or about 10,000 quadrillion dollars. So obviously that's not going to be the case, because if you brought all of that back to Earth right away, the metals market would crash and there'd be all sorts of economic havoc there. But the interesting thing is the idea that these asteroids have valuable materials that we could then utilize. Now, how do you mine that type of material on a low gravity body like this? It is not going to be an easy thing. It's not like the first graph there where you suck an asteroid in on one side and the space station comes out the other. It's not nearly going to be that easy. If you ever watched the TV show The Expanse, based on the novels of James S.A. Corey about humans, utilizing all the resources of the solar system, there's lots of miners out there. But it's going to take time. It's going to take decades to figure out how to mine asteroids with both robots and people. But the important thing is the fact that there's these resources out there. The same thing is true of the moon. You have high iron, high titanium lunar soils. Maybe you have helium-3 as a power source. You have water ice and permanently shadowed regions of lunar craters. You can take that water ice to drink, or you can separate the hydrogen and oxygen, the oxygen for humans to breathe, the hydrogen for rocket fuel. So there's a lot of resources that that are out there that could be utilized for humanity as we go and develop this. And this is a graphic that Planetary Resources made over a decade ago now about these whole things. So lots of opportunity, I think, is out there in the future if we choose to pursue that. So let me summarize by saying asteroids are the rocky remnants left over from the formation of the solar system. In January of 2017, NASA selected Arizona State University to lead the Discovery class robotic mission to the M-class asteroid 16 Psyche. And that's what you see there. That's the rotating shape model showing you the shape of the asteroid right now. And down here, this is the albedo map. It's a combined optical and radar albedo map. The important thing to see on this is there's different things in different areas. That means that there's differences on the surface. It's not one heterogeneous or homogeneous thing. There's different things. Some of these may be spots where there's metal exposed. Some of those may be spots where silicate is exposed. Maybe there's other things there. The point is, it's going to be different, and we will see something very interesting when we get there. So the Psyche mission, just like Dawn, uses solar electric ion propulsion to move through the solar system. We have our 3 instruments. The spacecraft launched on October 13th of 2023. We are cruising through the solar system right now. Our Mars flyby in May of 2026, arrival in August of 2029. So I invite you to stay tuned for that. We just created a new poster about Psyche and what its options might be. So if you scan this QR code, you can get the digital version of this. We haven't had time to print any yet, but I hope to have printed versions of that at some point later in the year. But you can still see the digital version right there. And I think this is a video. So there's no words on this, it's just sound, but this is a simulation of the spacecraft approaching the asteroid. So you see the blue flame of the ion propulsion, you see the solar panels deployed, and you see it going in to 16 Psyche. So first on the dark side, and then we'll get it to a point where it's going to start taking pictures of it. So this artist rendition shows you the metallic, supposed metallic surface with stuff is filling the topographic lows, and you see there's boulders there and stuff like that. Now, as we go into this fly through, I guarantee you the spacecraft is not actually going to get this close and fly through it like this, like some amusement park ride. This is just for the fun of it. But it's interesting to think about. You see, they have a lot more rocky material, sort of like the rubble pile. I think that's inspired by the rubble pile asteroids that we've been exploring up to this point, and then looking back at the metallic surface there. And who knows what the stuff is, the fine grained stuff in there. I imagine it's silicate. I bet there's a lot of silicate gunk that has fallen back on the surface there. And it's going to try and zoom in on the metal in this. And alas, yeah, there you go. It's palisade. So I don't know. I don't expect this is actually the palisade home world here, but it's a fun idea to think about. It's got to be more complex than that. I'm sure it is. So anyway, that's just what this video, and this video is online. If you go to if you just Google NASA PSYCHE mission, you'll take you to one of the websites. And if you look in the animations, you'll be able to download this video here. So I think that's, and then I'll just leave that there, that the planetary fleet, and I will go back there. So I will say thank you very much for your attention, and I would be happy to take questions. I see there's one over there.
Hello. You made a reference earlier to the OSIRIS-REx mission, okay? And I'm sure as most of us know, in April 13th of 2029, Apophis is giving us a flyby. It's my understanding that OSIRIS-REx was proposed to be reconfigured into OSIRIS-APEX, but now you may be fighting budget constrictions. Is that correct?
It is correct that the OSIRIS-REx spacecraft has been redesignated OSIRIS-APEX and is going to the asteroid Apophis to study that asteroid. As far as the NASA budget, we don't know what the NASA budget is for FY 2026 yet. There's been news in the press that this current administration wants to cut the NASA planetary science budget by 50%. So that's triggered a lot of us to write our senators and congressmen, and the Planetary Society. If you go to their advocacy webpage, they'll have the form letter on how to do that. I don't know that they would actually do that. I would think that the last thing that would be cut would be active flight missions that are flying in space that have not completed their nominal missions yet. PSYCHE is one of those. Lucy is one of those. Europa Clipper is one of those. And OSIRIS-APEX is one of those. So, but the way that you let your voice be heard, if you're a fan of solar system exploration, planetary exploration, is write to your senators and congressmen and say, we don't want to see the NASA science budget cut. And that's relevant for Earth science missions, it's relevant for heliophysics missions, et cetera.
Okay, I have one other question regarding that. Excuse me. At least initially, the observations of Apophis have indicated that it's going to be a miss as far as the Earth is concerned. But right now, it's my understanding that it's observing it is obscured because of the orbit of the sun. Is that correct? It's kind of behind the sun, and it's not supposed to have really get full visibility until sometime in 2027. And this OSIRIS-APEX mission was only designed to view Apophis like several days before it's supposed to do the flyby.
I do not know those details since I don't work on that mission. I think you're probably correct about some of that information. I have not heard anything about concern about that asteroid getting too close to Earth, But, that's why we send those missions out there, is to get better information on that. You should know that we do have NASA does have an Office of Planetary Defense, and it's looking for ways that might deflect asteroids. You might have remembered the DART mission from a couple of years ago that successfully altered the orbit of an asteroidal moon of asteroid Didymos. So we've proven that it is possible to change the orbital trajectory of small asteroids there.
If the asteroid has some water content and relative to its closest proximity to the orbit of the sun, can it outgas like a comet and change its trajectory?
Yes, I would think that is possible, depending on how much it has on board. I don't know that Apophis has had any determination that it has substantial volatiles on it, but yes, we've seen asteroids do types of degassing of things. Yes.
Okay, so ultimately, we don't know what trajectory is until it comes out from behind the sun.
Yeah, yeah.
What's going to happen to the spacecraft once it finishes orbit investigation?
Good question. Yeah, missions are only planned to a certain level at a time, and the primary mission or nominal mission of PSYCHE has been planned. So when we arrive there, we have a 24-month nominal mission, and what happens after that, it depends on how successful we have been at accomplishing our mission objectives. Did we catch all the data we want? Were there any problems? It also depends on whether the spacecraft is functioning. Does it still have fuel? Is it still able to generate solar energy to power the spacecraft? Usually the answer to that is yes. So then what the science team, what we will do is we will put in a proposal to NASA for a mission extension. And that mission extension could be for either dropping down to a closer orbit to gather additional data, or if we've completely accomplished all of our mission objectives and we have sufficient fuel, we could depart PSYCHE and visit someplace else in the solar system. This spacecraft is optimized for studying M-class asteroids, so it might be the case that we would go to another one. But that decision won't be made until near the end of the nominal mission in the 2031 timeframe, I bet.
Do you expect to see all the same metals on PSYCHE that we have on Earth and in similar proportions?
I think the answer would be yes, we expect to see similar metals, but they could be in similar proportions or different proportions. That's sort of one of the goals of the mission, is to go there and find out how similar or how different it is from Earth's core.
How long will it take the data to be transmitted back to Earth?
We transmit the data back using the NASA Deep Space Network, which is the system of radio telescopes. They're scattered 120 degrees around the planet. So one's in Goldstone, California, one's in Canberra, Australia, one's in Madrid, Spain. And so that no matter where a NASA spacecraft is in the solar system, it's always going to be, the Earth is always going to have an antenna in position to receive data from it. That system is used to return data from all of the missions, the rovers, the orbiters, the flybys, wherever they are. So it will just be transmitted back, and I don't know the actual travel time from PSYCHE. It's probably less than Jupiter, and Jupiter is between 18 and 21 minutes for a signal to get back. So we'll have a certain block of time each day when the spacecraft will transmit its data back. So we'll be getting data back daily during the nominal mission.
For PSYCHE and Lucy, I'm kind of curious as to the day-to-day right now. I imagine that at launch and when you get there is all very exciting, but is it mostly just turned off? Is go in the office once a week and see if it's still working, or what's happening?
Well, I go into the office every day, except on weekends, because there's always something going on. But yeah, we basically, for the imager is turned off, except when we do these periodic maintenance calibrations, and it's about every 6 months. But during that time, what we're doing is we are developing the calibration pipeline for it. We're doing the studies using telescopic data to better understand the asteroid, because there's new information coming in all the time. We're trying to figure out the nomenclature that we want to propose to the International Astronomical Union to name surface features. There's a lot of computer modeling being done of impact processes. There's analog studies of how to produce, metallic regoliths. There's a lot of, studies on how to understand the magnetic field of bodies like that. So there's a lot of precursor work that's going on right now while we're in this cruise phase, so that everybody and all the equipment, all the techniques, and the people are all ready for when we actually get there. So yeah, there's still a lot of activity going on.
And then for the Lucy mission, is that just a flyby or is it going to be orbiting any charge?
Multiple flybys. So the main belt asteroid Donald Johanson flyby, I think, is in about 2 or 3 weeks in mid-April. And then the starting the flyby of the Trojan asteroids, I think that starts around 2027, 2029, somewhere around. That'll be the first one, and it'll do multiple flybys. It's probably going to do at least 5 to 7 different asteroid flybys in those 2 camps.
Thank you.
Yes, somebody that would like to see maybe a small fraction of that 10,000 quadrillion dollars. I wonder if you have any thoughts about the different private companies that are interested in mining, if you have any insight into that.
I don't actually have much insight. That graphic from Planetary Resources was from quite a few years ago now. I do know that there are companies who are interested in that. I know that there was talk of a Earth orbiting satellite or near Earth mission that would image some of the near Earth asteroids, looking to see what kind of resources they might have. I think the techniques for mining on an airless body will probably be developed on the moon first. I mean, didn't the Firefly Blue Ghost lander that just landed on the moon have a drill to drill down the regolith on that? So I think it's already underway, and the moon is an ideal test bed, not just to go to Mars, but to do some of these other technological studies.
You mentioned the planetary cores cooling from the or solidifying from the inside out. Can you elaborate on that? I've never heard of that process.
Yeah, like the Earth's core. The Earth's core is freezing from the inside out. Solid inner core, liquid outer core. So yeah, normally objects you think they're going to be exposed to space is where it's colder, so you're going to be cooling from the outside in. But there's a possibility that for a planetary core, it could be freezing from the inside out, and the Earth's core is an example of that.
Are there any other sizable M-class asteroids?
16 Psyche is the largest. I think the second largest maybe is Cleopatra, and I don't know its number and I don't know its size. But there's a handful, at least a half dozen of these. Interestingly enough, 21 Lutetia that Rosetta visited is officially classified as an M class. But when we looked at it from that mission, there was nothing extraordinary about its appearance on the surface. So I think that and if Psyche looks like Lutetia, I will be very, very disappointed. But I don't think that'll be the case just based on the albedo map. Any other questions? I think there's one up here.
Oh, 1 second.
Be able to deal with that at all?
Yes. Yeah. What we do when we go to one of these bodies, as we approach, we do what is called a satellite search. So when we're still far out, we will be imaging the body and at a distance sufficient that we would see any type of asteroidal moon. We did that for Vesta. There wasn't any. We did that for Ceres. There wasn't any. Our best guess for Psyche, there won't be any, but we will do the search because obviously you don't want to go into a close orbit if you haven't identified something that you might run into. So yeah, we will look for that. Any other questions? All right. Well, thank you very much for your attention.